try to imagine taking an apple, right? And you cut it in half.
Okay, I'm picturing it.
So you take one of those halves and you cut it again. Now you have a quarter.
Yeah.
And you just keep going.
Right. Soon you have a tiny sliver.
Exactly. A sliver, then a speck of apple dust, and then, well, assuming you had an infinitely sharp microscopic knife, you get down to the individual molecules.
Oh, fundamental pieces.
Yeah. And for, 3,000 years, human beings have operated on this deeply intuitive assumption about that cutting process. We just assumed that if you kept cutting, you would eventually hit a bottom.
Right, a solid wall.
Exactly. You'd eventually hit a tiny, indestructible, solid block that simply could not be divided anymore. The ultimate piece of, well, stuff.
It is a very comforting thought, when you really think about it.
It really is.
Because it implies that the universe, no matter how chaotic or complex it gets, is ultimately constructed out of basic tactile building blocks. Like a cosmic Lego set.
Like a cosmic Lego set, yes. But today, we're going right into the deep end. We're going to look at a stack of modern physics papers, research summaries, and foundational theories that reveal a frankly terrifying yet incredibly beautiful truth about that cutting process.
And that truth is that there is no bottom.
There is no bottom. The solid world, as we intuitively understand it, just doesn't actually exist.
It's wild. And the sources we're looking at today, this extensive body of work, including compilations like The Last Division, they synthesize the findings of Nobel laureates and quantum gravity pioneers.
Right.
And the overarching consensus points to a massive, complete paradigm shift. We are moving from a universe of substance to a universe of pure process.
Pure process. I love that phrasing. And, the quest to find that ultimate indivisible particle has essentially forced modern physics to completely abandon the concept of the particle altogether.
Entirely.
So if you're listening to this deep dive right now and you're wondering how the chair you're sitting on could possibly not be made of solid stuff, that is exactly the journey we are going on today.
We're going to break it all down.
Literally. We are going to explore how matter, at its absolute fundamental level, dissolves entirely into energy. But to truly appreciate how radical this new view of reality is, we first need to look at the habit we are trying to break, right?
Oh, absolutely. We have a 3 millennia-old intellectual reflex that we really need to unpack here.
Yeah, historians of science actually refer to this as the ancient instinct.
No.
And it is deeply, deeply embedded in human psychology.
It is. If we trace the history of physics and chemistry, you can see exactly why we are so attached to this idea of the nesting doll.
The Russian nesting doll analogy.
Right, the idea that you just open one layer of reality and, oh, look, you find a smaller, harder object inside.
Let's walk through that timeline, actually, because the track record of this instinct is honestly staggering. If we go back to the year 1800.
The era of early atomic theory.
Exactly. John Dalton is formalizing all this, and the scientific consensus is solidifying around the idea that the molecule is the fundamental unit.
Right. You look at water, you break it down, and you get this discrete, indivisible unit that retains all the properties of the whole.
Right. So at that point, the molecule was the bottom of the nesting doll. It was the indivisible core.
But then technology improved.
As it always does.
Exactly. We developed cathode ray tubes. We got better at chemical analysis. And by the late 1800s, around 1890 or so, the scientific community realized that the molecule was actually a composite.
It was made of smaller, harder things.
Atoms. And the word atom itself literally comes from the Greek atomos, meaning uncuttable.
Uncuttable. That's so ironic now.
Right. So the scientific establishment adjusted and said, well, we were wrong about the molecule, but the atom, that is definitely the true bottom.
And that lasted for what, roughly 10 years?
Pretty much, yeah.
Because right around the turn of the 20th century, you have the discovery of the electron and then Ernest Rutherford conducting his really famous gold foil experiment.
Oh, that experiment is so elegant.
Let's talk about that methodology for a second, because it is so crucial to how we think about division. Rutherford didn't use a tiny knife to cut the atom, did he?
No. He used a radioactive source to fire alpha particles at an incredibly thin sheet of gold foil.
And alpha particles are, relatively speaking, heavy, fast-moving projectiles, right?
Very heavy and very fast. And the expectation, based on the models they had at the day, was that these projectiles would just punch straight through the atoms of the gold foil.
Because the atom was thought to be like a sort of soft, uniform sphere.
Right, a sphere of positive charge with just some electrons sprinkled in it, like a plum pudding.
A plum pudding model.
Yeah.
But instead, a very small number of these alpha particles bounced almost straight back.
Which was mind-blowing to them. Rutherford famously said it was as if you had fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you.
That quote is just incredible, and the only way that makes physical sense is if the atom isn't a soft, uniform sphere at all.
Exactly. Almost all of its mass had to be concentrated in a tiny, incredibly dense, solid center.
And just like that, the atom was cracked open. The nesting doll opened again, and inside, we found the nucleus.
And notice the methodology there.
Wait.
I think this is key. To divide the atom, Rutherford had to hit it with a high-energy projectile.
Right. You smash it.
Yes. This becomes the standard operational definition of division in physics. If you want to see what is inside a structure, you have to apply enough energy to overcome the binding force that is holding that structure together.
You hit it hard enough, the glue breaks, and you collect the smaller pieces that scatter away.
Precisely. You supply kinetic energy to overcome the binding energy.
And this brute force method, it works brilliantly for the next few decades, doesn't it?
It really does. In the 1930s, we built early particle accelerators. We take that nucleus, we hit it even harder, and the doll opens again.
The nucleus shatters into protons and neutrons.
Right. Then, by the 1960s and 70s, we build even bigger accelerators. We hit the protons at phenomenal speeds, and they break open to reveal quarks.
Okay, so if you are keeping score here, the historical pattern is perfect. Molecule to atom to nucleus to proton to quark.
5 distinct times over a century and a half.
5 times the scientific community thought they had found the fundamental thing, and 5 times hitting it with a bigger hammer revealed smaller things inside.
Which brings us to the ultimate anomaly.
Yes. We get to the quark. It's the 21st century. We know the proton is made of 3 quarks bound together.
Right.
We have the Large Hadron Collider, the 17-mile ring of superconducting magnets under the Swiss-French border, capable of generating just unimaginable kinetic energy.
The biggest hammer we've ever built.
Exactly. And we decide, okay, we want to isolate a single quark, put it under the metaphorical microscope, and see what the next nesting doll looks like.
We want to pull a quark away from its partners inside the proton.
And the universe simply says no.
Just flat out, no. And this is where our 3,000-year-old methodology violently breaks down.
Okay, let's unpack why.
To understand why, we have to look at the force holding those quarks together. You know, when we split molecules, we were fighting chemical bonds.
Right.
When we split the atom, we were fighting the electromagnetic force. When we split the nucleus, we were fighting the strong nuclear force.
Okay, keeping up so far.
But quarks interact via a very specific property governed by the strong nuclear force called color charge.
And when physicists say color charge, just to be super clear for anyone listening, we're not talking about visual colors like red or blue, right?
No, it's just a quirk of naming. It's a fundamental property, somewhat analogous to electric charge, but much more complex.
Because it comes in 3 types rather than just positive and negative.
Correct. And the theory that describes how this works is called quantum chromodynamics. The leading architects of this theory mapped out exactly why isolating a quark is impossible.
And it has to do with how the strong force behaves over distance, doesn't it?
Yes. Think about almost every other force we experience. Distance weakens the pull.
Like magnets. If you take 2 strong magnets and stick them together, pulling them apart for the first millimeter is incredibly difficult. You really have to strain your muscles.
Exactly. But once you get them an inch apart, the magnetic field drops off exponentially.
It gets easier and easier to separate them the further away they are. Gravity works the same way, right?
Right. But the strong nuclear force between quarks does the exact opposite.
Wait, the opposite?
Yeah. It exhibits a property called asymptotic freedom when the quarks are incredibly close together, meaning when they are right next to each other, they actually barely feel the force at all.
So they just move around quite freely.
They do.
Yeah.
But the moment you try to pull one quark away from the others, the force holding them together doesn't weaken. It intensifies.
Okay, the analogy that always comes to mind here isn't 2 magnets, it's a rubber band.
A rubber band is a highly accurate way to visualize it. The interaction between quarks is mediated by particles called gluons, which essentially form a flux tube between the quarks.
A flux tube.
Yeah, and as you pull the quarks apart, this tube stretches, and the tension increases dramatically.
So let's run the thought experiment for the listener. Imagine you have, like, microscopic tweezers, and you grab onto one quark.
Okay.
And you start pulling. You are putting massive amounts of energy into this system, stretching that rubber band. You pull harder, adding more and more kinetic energy.
Just draining.
Right. You just want the band to snap so you can walk away with your single isolated quark.
And the band does snap.
It does.
But you don't get your isolated quark.
And this is the crazy part. Why don't you get the quark?
Because of E equals mc squared.
Einstein's famous equation.
Precisely. That equation tells us that energy and mass are fundamentally interchangeable. They are two sides of the same coin.
Okay, I follow.
As you stretch that microscopic rubber band, the amount of energy you are storing in the tension of the strong force becomes immense. Becomes so vast that at the exact moment the band snaps, that stored energy instantaneously converts into new mass.
So the energy literally crystallizes into new matter.
Yes. The band snaps, and on the raw, broken ends of that invisible rubber band, the universe spontaneously generates a brand new quark and its antimatter partner, an antiquark.
This is just
It's
wild.
called color confinement. You started with a bound pair of quarks, you try to pull one away, and the result isn't a lonely quark. The result is that you now have two bound pairs of quarks.
So the energy you supplied to perform the division was just co-opted by the universe to manufacture new particles.
Exactly.
Okay, look, if you're listening to this and feeling deeply skeptical, it is totally justified because we talked about that ancient instinct.
Right.
If the pattern of finding a smaller nesting doll has been empirically right 5 times in a row, why shouldn't we just assume our microscopic scissors aren't sharp enough yet?
It's a fair question.
Right. Like maybe the rubber band snapping is just an engineering problem. Maybe in 50 years, we'll build a machine that can pull fast enough or clean enough to get the quark out. Why are physicists so convinced the chain stops here?
Well, it is entirely rational to suspect a limitation in our tools. But the mathematics of quantum chromodynamics, supported by decades of collider data, show us that this isn't a mechanical limitation.
It's not just a dull knife.
No, it is a fundamental firewall built into natural law. The mathematics dictate that the energy threshold required to physically isolate a color charge is always strictly greater than the energy required to create new mass.
Wow. So you cannot bypass this.
You can't. Nature refuses to allow a bare, isolated quark to exist in our current low-energy universe. The concept of pulling it apart to see what's inside is physically prohibited.
Okay, so we're at a dead end with our 3,000-year-old method. We can't use a bigger hammer. We can't physically cut the quark.
Right.
But physicists don't just give up. If we can't physically divide it, we have to look at what happens when matter undergoes an ultimate fundamental deconstruction. We basically have to change the definition of the word division.
We do. If mechanical division is impossible, we must define division functionally.
And what does that mean, functionally?
In this context, ultimate division is a finite sequence that ends in pure energy. We are looking for a process where the physical properties that define a thing like rest mass, physical boundaries, and structural identity just vanish completely.
And the research points to 3 established, proven phenomena in physics that show matter doing exactly this.
Yes.
And it's not science fiction. We can watch physical stuff unravel into pure energy. So let's look at the first phenomenon, which is probably the cleanest, most absolute proof of deconstruction. Annihilation.
Annihilation. This requires the introduction of antimatter.
Okay, break that down for us.
So every fundamental particle of matter in the universe has an antimatter counterpart. An electron has a positron, a quark has an antiquark.
And they're like mirror images?
Somewhat. These antimatter particles have the exact same mass as their normal counterparts, but their charges and certain quantum numbers are flipped.
And when a particle of matter meets its exact antimatter counterpart, it is not a gentle greeting.
No, not at all. If an electron and a positron collide, they annihilate each other.
But I want to be really clear about what annihilate means here. Because, you know, when 2 cars collide at high speeds, we say they are annihilated, but there's still a wreckage.
Right, there's debris.
There's twisted metal, shattered glass, maybe a fire. There are pieces left over. But when an electron and a positron collide, there is no shrapnel. 0 electron stuff remains. The matter simply ceases to be.
The physical entities with mass, charge, and structure entirely disappear. And in their place, radiating outward from the point of collision, are 2 or more gamma-ray photons.
Gamma rays. Light, pure electromagnetic energy.
Exactly. The mass of the electron and the mass of the positron have been 100% converted into the kinetic energy of the photons.
That is just incredible.
It is the cleanest example of division ending in pure energy. You didn't crack the electron open to find smaller gears.
Yeah.
You created a condition where the entire structural integrity of the matter unwound itself.
That unwinding concept is critical because it forces us to realize that an electron isn't a tiny bag holding light inside it.
No, not at all.
When it annihilates, it's not spilling its contents. It's more like, well, the matter itself was just a specific form that energy had temporarily taken. And annihilation is the process of returning that energy to its raw, unformed state.
That is a profound philosophical shift. It suggests that energy is the fundamental currency of reality, and matter is just one of the denominations it can take.
I love that. Energy is the currency. Okay, so annihilation is the clean case. But the second proof of deconstruction is a lot messier, and it's happening right now in particle accelerator.
Yes, melting case.
Right, what we might call the melting case. And it involves a state of reality called the quark-gluon plasma.
To create this plasma, physicists at facilities like the LHC in Europe or the Relativistic Heavy Ion Collider in New York, they don't use single particles.
They use heavy hitters.
Literally. They
Huh.
take heavy ions like the bare nuclei of lead or gold atoms, which contain hundreds of bound protons and neutrons, and they accelerate these massive clusters of matter to ultra-relativistic speeds.
Meaning extremely close to the speed of light.
Yes, and then they smash them head-on into each other.
The sheer violence of this collision creates an environment that basically defies human comprehension. We are talking about temperatures reaching several trillion degrees.
Trillion with a T.
Just to put that in perspective, the core of our sun is around 15 million degrees. A supernova core might hit a few billion. This collision generates a microscopic fireball trillions of degrees hot.
And under these extreme conditions of temperature and density, the ordinary rules of matter just break down completely. The protons and neutrons, which belong to a family of particles called hadrons, they don't shatter into tiny shards.
They undergo a phase transition.
They melt.
A phase transition, like ice melting into water, but on a subatomic level.
Exactly. The extreme kinetic energy effectively overrides the strong nuclear force that normally keeps the quarks confined. The boundaries of the individual protons and neutrons completely dissolve.
So earlier we talked about how you can't isolate a single quark in a cold vacuum because the rubber band snaps and makes more matter.
Right, color confinement.
But in this trillion-degree fireball, there's so much energy bouncing around that the quarks don't need to be confined in their little groups of 3 anymore. The rubber bands melt.
They become deconfined. And the result is a quark-gluon plasma. It behaves almost like a perfect, frictionless liquid composed of freely roaming quarks and gluons.
I think a good way to visualize what happens to the concept of a particle here is to think about a massive traffic jam.
Oh, that's a great analogy.
Right. Imagine you were in a helicopter looking down at a highway. At low speeds, you can see individual cars. You can see families in minivans, people in sports cars. You can clearly identify the discrete units.
Those are our protons and neutrons.
Exactly. But now imagine the speed limit on this highway is suddenly 1,000,000 miles an hour.
Pure chaos.
The cars are moving so fast and bumping into each other with such incredible kinetic energy that the distinct shape of a minivan or a sedan ceases to matter. The entire highway becomes continuous fluid blur of pure momentum.
The identity of a single car is completely lost in the overarching flow of energy.
Yes, that is exactly what happens to mass in the quark-gluon plasma.
It is. The rest mass of the quarks, the actual physical weight they possess, becomes essentially negligible. It's a tiny rounding error compared to the overwhelming kinetic energy of the plasma.
So they aren't things anymore.
No, the individual particles have lost their structural identity. They are no longer things. They are just localized ripples in a soup of pure thermodynamic energy.
And what's wild is that if you crank the temperature even higher, reality gets even less structured.
Yes, there is a theoretical threshold around 10 to the 16th Kelvin.
10 to the 16th.
At that unimaginable temperature, the fundamental forces of nature themselves start to lose their identities.
Wait, the forces lose their identity?
Yeah. In our everyday world, electromagnetism, which powers our electronics, and the weak nuclear force, which is responsible for radioactive decay, they act as two distinct forces with very different properties.
Right.
But at 10 to the 16th Kelvin, the energy is so intense that the mechanism that separates them breaks down. They unify into a single electroweak force.
So not only do the physical particles melt together, but the invisible rules that govern them melt together too.
Exactly. It's a process of symmetry restoration. And physicists believe that at even higher temperatures, this electroweak force would merge with the strong nuclear force.
Everything just becoming one.
And this isn't just a mathematical fantasy. This state of complete undifferentiation, where particles and forces are all melted into a single uniform energy state, was the actual physical reality of our universe in the first fraction of a picosecond after the Big Bang.
Man, that perfectly sets up the third proof of deconstruction. We've watched matter annihilate into light. We've watched protons melt into a fluid of pure kinetic momentum.
Right.
The third proof is the process running in reverse. It's called pair production.
Pair production is essentially the counterpoint to annihilation.
Okay, how does it work?
Well, if you have a photon, a particle of pure electromagnetic light, and that photon possesses an exceptionally high amount of energy, it can interact with a heavy nucleus and spontaneously transform into an electron and a positron.
Pure light just turns into matter.
Yes. The energy of the wave collapses into two particles with mass, physical dimensions, and electrical charge.
You know, this blew my mind when I first really thought about the implications.
It's hard to wrap your head around.
Because if pure energy can spontaneously decide to organize itself into an electron, that answers a massive philosophical question. It means energy isn't just a property that matter has. Energy exists before matter does.
Logically and temporally, energy is the prerequisite. Matter is contingent upon energy.
The metaphor that really solidified this for me is crystallization. We should stop looking at a piece of matter, like a quark or an electron, as a tiny brick. We need to view it as a temporary, localized crystallization of energy.
That framing aligns perfectly with modern physics.
It's like ice, right?
Exactly. When water gets cold enough, the thermal energy drops, and the molecules arrange themselves into a rigid, stable pattern. Ice.
And it looks completely different.
It looks fundamentally different from liquid water, but it's the exact same fundamental stuff, just in a lower energy, highly structured state.
So when we talk about dividing a quark, our old 19th century brains picture taking a hammer and smashing a crystal into smaller shards.
Right, looking for the smaller pieces.
But what physics tells us is that true division is taking a blowtorch and melting the crystal back into the liquid it formed from. You aren't shattering a solid, you are dissolving a pattern.
And this realization is what finally breaks the nesting doll instinct permanently.
It has to.
If matter keeps dissolving into energy, then our foundational model of the universe cannot be based on little hard spheres bouncing around in an empty void. The universe isn't a giant billiard table.
But if there are no billiard balls, how do physicists actually calculate anything? I mean, how does modern math handle a universe that isn't made of stuff?
It requires a completely different mathematical framework, one that discards the idea of the particle as the primary citizen of reality.
And what is that framework?
It's called quantum field theory, or QFT. And it is, without exaggeration, the most successful, rigorously tested scientific theory in human history. It underpins everything we know about particle physics.
Okay, let's slow down and really dissect the QFT paradigm shift, because this is the moment where everyday reality feels like it turns inside out.
It really does.
What exactly is a field? Let's start there.
Historically, a field was just a mathematical tool to explain action at a distance. Think of Michael Faraday in the 1800s, sprinkling iron filings around a magnet.
Oh, yeah, and they make those cool patterns.
The filings align in these beautiful curving patterns. Faraday proposed that the magnet was projecting an invisible field of force into the space around it. The field wasn't made of matter, but it possessed energy and could influence matter.
Right, it's like a way of mapping out where the force is strong and where it's weak.
Exactly. But quantum field theory takes that concept and elevates it to the ultimate physical reality. In QFT, the fundamental building blocks of the universe are not particles. They're continuous dynamic fields that permeate every single point in space and time.
Wait, everywhere. There are no gaps.
None. There is an electron field that exists uniformly throughout the entire universe. It is flowing through the room you're in right now.
That's crazy to think about.
There is an up quark field. There is a down quark field. There is an electromagnetic field. These invisible interwoven fields are the actual substrate of reality. They're the water in the ocean.
Okay, so if reality is just these invisible fields layered on top of each other, what is a particle? Because when I look closely at a speck of dust under a microscope, I see structure. I see particles.
In QFT, what our instruments measure as a particle is nothing more than a localized vibration, a highly energetic excitation in its respective field.
An excitation.
Yeah. Yes. An electron is just a tiny quantized ripple in the universe-spanning electron field. A photon is a ripple in the electromagnetic field.
Let's use an ocean analogy because it really clarifies why the old idea of division fails.
Sure.
Imagine you are standing on the beach watching a massive wave roll in. Asking if a cork can be divided to find its solid core is like pointing at that wave and asking, can I divide this wave into smaller pieces of wave stuff? What is the solid block that makes up the wave?
Right. The question itself is structurally flawed. A
Yeah.
wave isn't made of wave stuff. The wave is just an energetic event happening to the water.
You can't scoop up a bucket of wave and take it home. You just have a bucket of water. The energy moved on.
Precisely.
You can certainly make smaller waves. You can drop two rocks in a pond and watch the ripples crash into each other, creating incredibly complex, chaotic interference patterns. But no matter how intricate the splashing gets, the underlying reality never changes. It is always just the continuous medium of the water and the energy moving through it.
And, one of the foundational thinkers in this space argues that our adherence to the particle concept is essentially an evolutionary hangover.
An evolutionary hangover.
Yeah.
How so?
Well, human brains evolved on the plains of Africa to interact with medium-sized solid objects, rocks, trees, animals.
Things we could pick up or run away from.
Exactly. Our neurology is hardwired to view the world as a collection of discrete things with clear boundaries. But the mathematics of quantum field theory strongly suggest that there are no particles in any traditional physical sense. There are only continuous fields and the energetic processes that excite them.
If you're listening right now, take a second to look at the device you are playing this deep dive on. Your phone, your computer, your headphones. It feels solid in your hand.
It does.
It has weight, it has mass, it has boundaries. But according to the most precise, battle-tested physics humanity has ever developed, that device is not made of microscopic solid blocks. It is not a box of subatomic Legos snapped together.
No, it is a symphony of vibrations.
A symphony of vibrations. Your device, your hands, the air you are breathing, it is all made of localized, persistent excitations in invisible fields that stretch across the entire cosmos. It is much more accurate to compare your phone to a complex chord being held down on a piano than to a collection of tiny pebbles.
The invisible quantum fields are the strings. The energy of the universe is the hammer striking those strings, and the matter we interact with is just the music that results.
Man, that reframes the whole mission of our deep dive. If everything is ultimately a process, a vibration in a medium, then the search for the final bottom nesting doll is officially over.
Because the bottom doesn't exist.
There is no foundational grain of reality. The universe isn't an empty void that happens to contain objects. The universe is the fields. The activity itself is the reality.
Beautifully said.
But this all sounds incredibly poetic and honestly a bit mystical.
It can feel that way, yes.
But we are talking about hard science here. So I have to ask, do all physicists actually walk around believing that things don't exist? Is this a settled fact? Or is there a debate about how we are supposed to interpret the math of QFT?
Oh, there's a fierce debate. And it cuts right to the heart of philosophy and physics.
Okay, let's hear it.
The underlying mathematics of QFT are universally agreed upon because they make predictions that are accurate to over a dozen decimal places. But what those equations physically mean about reality is definitely up for interpretation.
And the sources we're analyzing broadly categorize this debate into two distinct camps.
Right. Interpretation A and interpretation B. Let's look at interpretation A first, the fundamentalist view.
The fundamentalist view.
This is the conservative, pragmatic approach. It says, look, a quark behaves like a point particle in our detectors. It has specific quantum numbers. Therefore, a quark is a truly elementary particle. It has no internal structure. The chain of division ends permanently with the quark, and we should just accept it as the fundamental unit of matter.
So in this fundamentalist view, the quark isn't made of energy. Rather, energy is just a property that the quark carries, like a hiker wearing a backpack.
Exactly.
The hiker is the particle, the backpack is the energy, and they are distinct concepts.
Yes. It preserves our intuitive desire for reality to be made of stuff. And to be perfectly clear, this is the standard view taught in almost every undergraduate physics textbook.
Because it works.
It is mathematically consistent with the vast majority of our day-to-day experimental data. The authors of our sources call this view boring but defensible.
Boring but defensible. All right, and then we have interpretation B, the process relationalist view.
This is the radical field-centric view we've been building toward. The process relationalist argues that calling a quark an elementary particle is a fundamental category error.
A category error.
It is applying the wrong linguistic and conceptual framework to reality. There are no tiny things. There are only fields, the mathematical symmetries that govern them, and the flow of energy. What we mistakenly label a quark is just a stable, persistent excitation pattern, a standing wave in the field.
So under interpretation B, division isn't splitting a thing. Division is the process of altering that excitation mode, bleeding off its kinetic energy until you eventually quiet the field back down to its featureless, flatline ground state.
You smooth out the ocean.
You smooth out the ocean. But I want to push back here because if I'm a student trying to understand the world, interpretation A, the fundamentalist view, with the tiny particles carrying backpacks of energy, it works.
It does work for most things.
Right. It lets engineers build quantum computers. It lets us design MRI machines. It lets us run nuclear power plants. It's safe and calculable. Why should we bother adopting this incredibly weird, counterintuitive process relationalist view?
That's a very common objection.
Does it actually matter if reality is a tiny solid ball or a localized field vibration if the math outputs the same answers for our daily lives? Isn't interpretation B just a bunch of theoretical physicists engaging in academic navel-gazing?
It's an excellent challenge. Why adopt the mind-bending ontology if the boring one builds good lasers?
Exactly.
The answer is that the fundamentalist view only works under normal conditions. But when you push the universe to its absolute physical extremes, interpretation A begins to philosophically unravel.
Like the quark gluon plasma we talked about earlier.
Precisely. If a quark is a fundamental, indestructible, solid thing, how do you explain a macroscopic state where trillions of these indestructible things melt into a single cohesive liquid where their individual mass and identity vanish?
Ah, I see.
A traffic jam of cars can't melt into a single giant flowing car, but waves on an ocean can absolutely merge into a massive surge of water.
The wave analogy handles the extreme conditions effortlessly, while the particle analogy breaks down completely.
Furthermore, interpretation B is deeply and fundamentally consonant with the actual axioms of quantum field theory. When physicists write down the foundational equations of the universe, they do not write equations for particles.
They write equations for continuous fields.
Interpretation B simply takes the mathematics at its word. It refuses to force a comforting 19th century mechanical bias onto 21st century mathematics.
Okay, I buy that. If we want to truly understand the architecture of the universe, we can't just rely on approximations that are convenient for high school chemistry textbooks. We have to look at the edge cases.
We have to look at the extremes.
So let's accept the challenge. Let's side with the process relationalist. We believe matter is just a vibration. How do we definitively, empirically prove it?
That is the million-dollar question.
If ultimate division means unexciting a matter field until it flatlines into pure energy, how hard do we have to hit a quark to make it completely forget it's a quark?
Well, this is where we leave the realm of current experimental capability and look at the absolute theoretical limits of the universe. To witness ordinary matter, just a regular piece of a proton, not antimatter, completely dissolve its identity into pure energy, we have to concentrate an incomprehensible amount of energy into a single quantum point.
We have to push the local temperature so high that the field fluctuations become violently extreme.
And physics gives us a precise number for this threshold, the Planck energy.
The Planck energy. Okay, break down the numbers for us.
The Planck energy scale is approximately 1.22 times 10 to the 19th GeO. That stands for gigaelectron volts.
To give some context to the listener, an electron volt is a very small unit of energy used in particle physics. It's the amount of kinetic energy a single electron gains when it accelerates through 1 volt of electricity.
Right.
A gigaelectron volt is a billion of those. So we are talking about 12 quintillion gigaelectron volts concentrated into a space smaller than a single proton.
The numbers are staggering. Let's compare it to the Large Hadron Collider.
The biggest machine on Earth.
The LHC uses 17 miles of superconducting magnets, chilled with liquid helium, to a temperature colder than outer space, just to accelerate microscopic particles to around 13,000 to 14,000 JeV.
So the biggest, most expensive, most power-hungry machine human beings have ever engineered tops out at around 14,000 J. And the Planck energy is 10 to the 19th J.
Yes. The Planck energy is roughly a quadrillion times more powerful than the absolute maximum capacity of the Large Hadron Collider, 15 orders of magnitude.
What happens to the laws of physics if you actually manage to pump a quadrillion times the energy of the LHC into a single particle?
Reality breaks.
Thus breaks.
At the Planck scale, the 4 fundamental forces of nature are forced into parity. In our everyday world, gravity is incredibly weak compared to electromagnetism or the strong nuclear force. That's why a tiny fridge magnet can defy the gravity of the entire Earth and hold up a piece of paper.
Right.
But at the Planck energy, gravity's strength amplifies exponentially until it is just as strong as the other forces.
And when gravity gets that strong at a quantum level, the actual fabric of the universe starts to fail. This connects to theories on quantum gravity, doesn't it? The environment at the Planck scale is described as space-time foam.
Space-time foam, that's right. Because gravity is the geometry of space-time itself. When quantum gravity becomes dominant, the smooth, continuous fabric of space and time begins to violently boil and warp.
The boils.
The concepts of here and there or before and after lose their physical meaning entirely.
So if you inject a quark with the Planck energy, it's not just that the quark melts, it's that the actual space the quark occupies is boiling so violently that the distinction between a particle, a field, and the geometry of the universe completely evaporates.
They become indistinguishable.
You can no longer tell if you are looking at an object, a wave of pure energy, or just an incredibly tight wrinkle in the fabric of reality itself. It is pure chaos. Pure potential.
Is the ultimate ground state of existence. All structure is erased.
Logistically, if we wanted to build a machine to prove this process relationalist view, to see matter unravel into space-time foam, we would need a particle accelerator capable of hitting 10 to the 19th JeV. What would that engineering project actually look like?
The math provides a very humbling reality check here. Because of how magnetic containment and particle acceleration work, to reach the Planck energy using our current technological paradigms, you couldn't use a 17-mile ring in Switzerland.
No, I imagine not.
You would need to build a particle accelerator roughly the size of our entire galaxy.
A ring of superconducting magnets spanning 100,000 light-years across the Milky Way.
It is a profound physical impossibility. As a species, from a strictly experimental standpoint, witnessing the final deconstruction of matter is forever out of our reach. We will never build the machine.
But, and I love this part, there is a twist. And it's probably the most awe-inspiring realization in modern physics.
The twist is that we don't have to build the machine, because nature already built it.
The universe itself was the collider?
Precisely. We can never create these conditions in a laboratory today, but these conditions were the ambient reality of the cosmos in the past.
If you rewind the clock.
If you rewind the expansion of the universe, everything gets closer together, denser, and hotter. If you trace it all the way back to the incredibly brief fraction of a second after the Big Bang, specifically the first 10 to the negative 43 seconds of existence, a sliver of time known as the Planck epoch.
The entire universe, all the mass and energy that currently spans tens of billions of light years, was compressed into an unimaginably hot, dense point operating exactly at the Planck energy scale.
Exactly. And in that era, in that primordial fire, there were no atoms, there were no protons, there were no quarks. The universe was far too energetic for the fields to stabilize into those localized vibrations.
Matter simply did not exist.
Only a unified, featureless, infinitely dense ocean of energy existed. The ultimate proof that interpretation B is correct, that energy precedes matter, and that matter is just cooled down, crystallized energy, lies in our cosmic origins.
That is just stunning.
Everything you interact with, everything your body is made of, are literally the chilled remnants of that initial structureless fire.
The fields cooled down, the energy settled, and the symphony of localized vibrations began.
It's beautiful, isn't it?
Let's pull all of this together. We started with a quest that humanity has been obsessed with for 3,000 years. From the ancient Greeks looking for the unbreakable atomos, to the chemists of the 1800s classifying molecules, right down to the mid-century physicists cracking open the nucleus to find protons and eventually quarks.
We spent millennia wielding sharper and sharper knives.
Looking for the ultimate solid building block of reality.
And the conclusion that modern quantum physics forces us to accept is that there are no blocks. The quest for fundamental substance ends with the realization of pure process.
We have moved entirely away from a universe made of stuff to a universe made of activity. Matter is a temporary, localized phenomenon. It is a persistent vibration in an infinite, interconnected web of quantum fields.
And if you are listening to this right now, I hope this gives you a profound, almost hallucinatory new lens through which to view your daily reality.
It truly replaces a static, dead universe with an incredibly dynamic, active one.
It does.
The next time you walk up to a heavy wooden table and knock on it with your knuckles, I want you to pause and really think about the physics of what is happening. You aren't hitting solid stuff. The solidity is an illusion.
Your hand is interacting with locked up energy. The electrons in the atoms of your hand are repelling the electrons in the atoms of the table via the electromagnetic force field.
Right.
The mass of the wood is just the kinetic energy of gluons binding quarks together in a localized quantum dance.
The table is just energy that has temporarily forgotten how to be free. It is an incredible, almost magical way to walk through the world. Every solid object you touch is just a frozen melody in a quantum field.
I couldn't have said it better myself.
But before we wrap up this deep dive, I want to leave you, the listener, with one final thought to mull over, something that builds strictly on the physics we've just discussed.
Okay, lay it on us.
We established that in the very first 10 to the negative 43 seconds of time, the universe was nothing but featureless, unified energy. And as the universe expanded, the ambient temperature cooled. And as it cooled, that raw energy crystallized into the complex matter we see today.
The quarks, the electrons, the atoms, the stars, the wooden tables.
Right, they're all localized excitations that formed specifically because the universe cooled down enough to allow those intricate vibrational patterns to stabilize.
That is the thermal history of the cosmos in a nutshell. Expansion leads to cooling, which allows for structure.
Right. So if we know that the universe is continuing to expand, driven by dark energy, and it is continuing to cool, well, what happens at the very, very end of time?
Ah, I see where you're going with this.
Could there be a distant future threshold where this entire thermodynamic process runs in reverse? As the universe expands toward infinity, becoming unfathomably cold, diffuse, and isolated, could there be a point where these temporary, localized crystals of matter simply lose the ambient energy required to maintain their patterns?
A cosmic unraveling, a state of maximum entropy where the fields lose their capacity to sustain complex excitations.
Yes, a point where the vibrations in the fields just, well, quiet down, where proton decay eventually takes hold, where every quark, every electron slowly unexcites and dissolves back into the pure, formless, flatline energy state from which it was born in the Big Bang.
It's entirely possible based on the models.
If that happens, it would mean that this entire incredible universe of solid objects, of glowing galaxies, of rocky planets, of complex biological life, this entire era of matter is nothing but a brief, temporary season in the endless, dark lifespan of the cosmos. A momentary frost on the window pane of eternity, destined to eventually melt away back into the void.
Wow, it is a beautiful, terrifying thought.
And it reminds us of how incredibly lucky we are to be alive in the season of structure. But for now, that's where we'll leave it. Keep wondering, keep questioning, and we'll see you on the next deep dive.